Hey, chemistry enthusiast. If you are an industrial chemist, you are a scholar in chemistry, in advanced chemistry. If you are looking at modeling or simulation or making simulations of chemical kinetics in Python, this is your video. So we are going to be looking at three rate laws, and one is the zero order reaction, whereby the rate is equal to the K, whereby K is the rate constant. So we are saying that the rate is constant and independent of the concentration of the reactant. Number two, these formulas are known. So if you have a reactant A, if you're talking about first order reaction, then its rate law will be rate equal to K times concentration of A. And the rate here means that it is directly proportional to the concentration of the reactant. Now, the second order reaction says that the rate of the reaction is directly proportional to the square of the concentration of the reactants. If they are two, then here we would be having concentration of A, for example, and concentration of B. This can be, for example, the reaction between sulfur trioxide, the reaction between sulfur dioxide and sulfur oxide form sulfur trioxide, a very important process in the formation of large-scale production of sulfuric acid. So the rate is proportional to the square of the concentration of the reactant. So where you have two reactants, then this is what it would actually be. So if we're talking about sulfur dioxide and oxygen, then you'll have the concentration of oxygen, you'll have the concentration of sulfur dioxide. But if you have only one reactant, for example, if the decomposition of hydrogen peroxide follows a second order reaction, then you would have a single reactant, meaning this would be K then times the concentration of hydrogen peroxide squared. So we are going to be doing these formulas, manipulating them in a computer software and seeing the output. What do these basics help? In case you want to deal with complex situations where you cannot easily look at the relation between the two, or you cannot understand the rate of reaction in such complex scenarios. For example, in medical, you might be looking at modeling the rate of reaction of penicillin and beta-lactamase, which is an enzyme that attaches itself on penicillin on the beta-lactam ring, thereby inactivating penicillin or forming what we call an inactive complex where penicillin is rendered useless. So if you want to look at such a reaction, look at the rate and then maybe be able to control it, then you need to use sometimes computer softwares to be able to see this process done as quickly as possible. So let's go to Python, and we are using our editor. The environment that we are using, or the integrated development environment that we are using, is Visual Code or VS Code. So what we are going to do, I've already provided a frame of how we can do this reaction. Or how we can model this process. So what we are going to be doing is to just add in what is missing. So these are the important libraries. Obviously, numerical Python or NumPy is important in manipulating data. For example, if you want to make an array, you want to make a matrix, or you want to make a list of values, NumPy is very important. If you want to do plotting or visualizing the output in terms of a plot, then we use Matplotlib, .pyplot. So NumPy is, we import it as NP. So we import also matplotlib.pyplot as PLT. Now we're going to be defining the rate zero order. So we are going to be looking at three equations like we earlier on we saw in our process here. We are looking at three rate laws. So we have this, that, and that. So these are the three that we must put in our program. So we are beginning with a zero order reaction. So we are going to have a model or a function that defines or that calculates the rate of reaction for a zero order reaction. So what are the inputs? So obviously the input is going to be concentration, as we had earlier on seen. It is going to be the concentration because you saw that the rate is a function of concentration of the reactant and the rate constant. So we are going to put our rate constant there. Then this is just a description, and so what is this function going to return? It is going to be returning k, obviously, times. Now for you see, for a zero order, it has nothing here, so it has to return. If we want to be general, remember here we have a, here we have a, so we must produce an array here of values that are not going to affect our output. And the array of values that we can use here are ones. So we shall be getting k times 1, k times 1, k times 1, k times 1, and so on and so forth. So to do that, we are going to use NumPy. So NumPy.ones like. This function is going to help us to produce ones that are going to be the same and throughout being multiplied into k, and then the output, those values then fed into the model, and we can get the rate of the reaction. So how can we complete that? So we are going to say this array that we are going to produce, it should be like that of concentration. So we're going to produce an array, okay, of ones that is the same as that one of concentration of A. So remember, concentration of A, we are going to use it down here. But for this one, you don't need to multiply it because the rate of the reaction is independent of the concentration of the reactant. So we have finished that. So we go to the second model. The second model also requires the input as concentration of A and K, and then it will be returning K times the concentration of A because that's what we have. Yes. Then we go to second order. Second order also, the input is concentration of A, and then an input is K. So it is going to be producing K times concentration of A squared. So this is how we write the square, or if it was cubed, then we would just put 3, but it is squared. So let's proceed. We have finished that. Now let's define initialize our parameters. The K, the constants for zero order, first order, and the second order, we are taking it to be 0.1. And let's proceed. Obviously for first order, the K is in units of per second. The rest for zero and second order in moles per liter per second. So let's look at the range of concentrations. So the range of concentration values, okay, the range of concentration of values. Remember, we defined here that the array that we are going to produce should be like, they are going to be ones, but like those, but the array should be like that one of concentration of A. So now we need to define the values of concentration of A. So we are going to be starting from, we are going to produce 100 values beginning from 0.01 to 1. Then we are going to also calculate the rate of reaction for each order. So for 0, remember we have already defined this function, so I'll just put rate 0 order, then concentration values, A values that we have created here, then comma K0. For first order, the same. For second order, the same. So now what we are going to do, we got plots. So in plotting, we need to look at what are we plotting against what. So x-axis is going to be having the concentration of A, which is the reactant, and then the y-axis is going to be having the rate of reaction. So we are going to say we are going to use PLT or plot dot x label. Okay, we are going to label the x-axis first of all as, we are going to label the x-axis as, we say, the concentration of A, and this should also indicate units in moles per liter. Then we are going to do PLT dot y label, that is labeling the y-axis, and we are going to say rate of reaction, and this is going to be in moles per liter per second. And finally, we need to put the title of our plot. So PLT dot title. So what we are going to say is that it's going to be a graph of rate of reaction against or versus, okay, versus concentration. Okay, concentration taking 0 order, 0 first and second order. Let me say second order reactions. So then we first finish here. So 0 order reaction plot. The 0 order reaction plot, we said it is going to be a plot of concentration of A values. So the rate that we have here, we have rate 0. Remember, all this has been defined because this is on x-axis, this is on y-axis. So we are putting it in form of like coordinates x, y. So plot concentration A values, which is on the x-axis, then rate 0, which is on the y-axis. Then we do the same. We are going to do the same for even the first order. So here what we do, we put rate first because that's what the function up there says. Then we do the same for second plot and we say rate second. So once we are done with those, because if they are not there, then you'll have an empty plot. But since we have defined now each the plotting for each and every rate, the 0, first and second, then here it is very okay. So we can go ahead. This is concentration of A. So we can go ahead and plot this. So let's run this. Let's look at the output. So ladies and gentlemen, this is the output. The legend has been shown. The concentration of the reactant is on the x-axis, and on the y-axis we have the rate of reaction. Then this is our heading or title of this plot. So this one, the blue one, shows zero order. The brown one is, so they are all showing zero order. Let's go back and do the editing. So the problem could be coming from, the problem is coming from here. So this is going to be first order, then this is going to be second order. So we save and run again. When we run again, you can see that the zero is the blue one. First is obviously a constant, whereby the rate is equal to, is directly proportional to the concentration of the reactant. And then this one is following a parabolic path, whereby the rate is directly proportional to the square of the concentration of the reactant. So ladies and gentlemen, this is again another video that we have done, and I believe you enjoyed. So I'll share the link to the rest of the videos in our description, but also I will share the code so that you can pick it, go and use it the way you want. Thank you so much.